Welcome. Adaptation of the Brain That Changes Itself. Stories of Personal Triumph from the Frontiers of Brain Science by Norman Doidge, MD. This book explores the revolutionary discovery of neuroplasticity, revealing that the human brain is not a rigid, hardwired machine, but a dynamic, self-adapting organ. Through powerful case studies and scientific breakthroughs, it uncovers how we can rewire our brains to heal from trauma, overcome lifelong learning disabilities, conquer deep-rooted obsessions, and sharpen our minds as we age. Its purpose is to redefine our understanding of human nature, showing that the brain's inherent ability to change itself is the key to both our greatest vulnerabilities and our ultimate triumphs. Chapter 1. A Woman Perpetually Falling, rescued by the man who discovered the plasticity of our senses. There is a profound terror in the sensation of falling, a primal alarm that bypasses all logic and grips the deepest regions of the nervous system. For Cheryl Schultz, this terror is not a fleeting nightmare. It is her permanent, waking reality. When she attempts to stand without leaning heavily against a solid surface, she mimics the frantic, desperate choreography of a tightrope walker on the verge of a fatal plunge. Her arms flail outward, her head lists and snaps back, and her torso jerks violently. It appears as though an invisible gang of assailants is violently shoving her from every direction. Yet both of her feet remain planted firmly on the floor. The sensation of plummeting never ceases. Even when she yields to the exhaustion and collapses onto the carpet, the relief of solid ground eludes her. She experiences the horrifying illusion that the floor has dissolved, giving way to an endless, bottomless abyss. Cheryl's torment is rooted in the catastrophic failure of a sensory system most of us completely ignore: the vestibular apparatus. Nestled deep within the inner ear, this delicate organ, consisting of 3 fluid-filled semicircular canals, is the biological gyroscope that anchors us in 3-dimensional space. It constantly detects the subtle shifts of gravity and momentum, transmitting rapid-fire electrical signals to a specialized cluster of neurons known as the vestibular nuclei. These brain centers unconsciously command our muscles to adjust, keeping us upright, and seamlessly coordinate with our eyes so we can track moving objects without our vision blurring. Aristotle famously catalogued the 5 human senses, completely overlooking balance, precisely because a healthy vestibular system operates with such flawless, invisible precision. For Cheryl, that precision was annihilated in 1997. Following a routine surgery, she developed an infection and was administered gentamicin. While highly effective, this antibiotic harbors a dark, toxic side effect. If used excessively, it acts as a poison to the inner ear. Cheryl was administered the drug far beyond the safe threshold. Almost overnight, she lost nearly all of her vestibular function. She became part of a tragic, marginalized group of gentamicin casualties who refer to themselves as wobblers. The fallout was absolute. She lost her demanding career in international sales. Her vision degraded into a chaotic, bouncing blur whenever she moved her head, rendering her unable to read or safely navigate her environment without her eyes interpreting the world like a violently shaking video camera. She developed a profound, unnameable anxiety, living on constant high alert. The sheer cognitive energy required simply to keep her body from toppling over hijacked her mental resources, leaving her perpetually exhausted and struggling with memory and concentration. Mainstream neurology offered a bleak, unyielding verdict. Her inner ear was permanently destroyed, and because the brain's processing centers were supposedly rigidly defined and unchangeable, her condition was incurable. She would fall forever. Yet, the dogma of the rigid, machine-like brain was about to be challenged in a laboratory in Wisconsin, led by the brilliant and unconventional neuroscientist Paul Bach-e-Rita. Cheryl sits in Bach-e-Rita's lab, surrounded by a team of researchers, preparing to test a prototype that looks like a makeshift prop from a science fiction film. She places a modified construction hard hat on her head. Embedded within the hat is a highly sensitive accelerometer, a sensor designed to detect the exact angle and momentum of her head's movement in space. This sensor is wired to a computer, which translates the movement data into electrical impulses. These impulses are then routed to a thin, flexible plastic strip resting directly on Cheryl's tongue. The strip is studded with 144-minute electrodes. As she tilts her head forward, the computer sends a corresponding wave of tiny, effervescent electric shocks resembling the prickle of carbonated bubbles across the front of her tongue. If she leans back, the sparkling sensation rolls toward the back of her mouth. The device bypasses her dead inner ear entirely, sending spatial orientation data directly into her brain through the touch receptors of her tongue. With the hat secured and the tongue display humming with data, Cheryl closes her eyes and slowly pulls her hands away from the safety of the table. The frantic, jerky compensations vanish. Her body ceases its desperate wavering. For the first time in 5 agonizing years, the terrifying sensation of free fall evaporates. She stands perfectly still, anchored and serene. Overwhelmed by a sudden, miraculous peace, she begins to weep. For 20 minutes, she holds her balance effortlessly, her brain performing an astonishing feat of neurological alchemy. It is intercepting tactile signals from the tongue, normally routed to the sensory cortex for the feeling of touch, and seamlessly decoding them as precise data regarding gravity and balance. However, the true miracle of brain plasticity reveals itself when the machine is turned off. Cheryl removes the tongue strip and takes off the cumbersome hat. According to the strict rules of conventional neurology, the moment the artificial sensory input is severed, she should immediately revert to her helpless, wobbling state. Instead, she grins, closes her eyes, and remains perfectly upright. She lifts one foot, balancing easily on the other. She is standing on her own. The researchers call this the residual effect. Initially, after only a minute of wearing the device, Cheryl retained her balance for 20 seconds. But as her time on the machine increased, the residual periods of normalcy stretched exponentially. On this day, a 20-minute training session buys her hours of absolute vestibular peace. She playfully dances around the laboratory, picking up objects from the floor, reclaiming the simple, beautiful mechanics of human movement. Bach-y-Rita theorizes that this residual effect is the ultimate proof of neuroplasticity at work. Cheryl's damaged inner ear is not entirely silent. It is emitting chaotic, noisy signals that scramble her brain's equilibrium. The tongue device provides a strong, clear, artificial signal that cuts through the noise, allowing her brain to reinforce and unmask secondary, dormant neural pathways. Like a driver discovering hidden country roads when a major bridge collapses, Cheryl's brain is bypassing the damaged neural superhighways and strengthening new connections. The more she trains with the device, the stronger and more permanent these new pathways become. This triumph is not an isolated anomaly, but the culmination of a lifelong rebellion by Paul Bach-y-Rita against the prevailing scientific establishment. Decades earlier, in 1969, he published a revolutionary paper demonstrating a tactile vision machine that allowed congenitally blind individuals to perceive the visual world. By outfitting a modified dentist's chair with 400 vibrating stimulators resting against a blind person's back and connecting it to a large camera, he translated visual scenes into physical vibrations. With practice, the blind subjects stopped feeling vibrations on their skin and began experiencing three-dimensional visual space, learning to recognize faces, discern objects, and judge perspective. Bach-y-Rita's core philosophy was breathtakingly simple, yet profoundly subversive. It is not our eyes that perceive the world, but our brains. The avenue through which a sensation enters the nervous system is fundamentally irrelevant to the brain. Consider a blind individual navigating with a cane. As he sweeps the tip back and forth, he gathers tactile data through a single point of physical contact in his hand. Yet, what he consciously experiences is not the pressure of the cane against his palm, but the spatial reality of the room, the precise location of chairs, walls, and doorways. The physical receptor on the skin loses its identity in this process, functioning merely as a biological relay station, a data port for incoming environmental information. Recognizing that both the retina and the skin are essentially two-dimensional sheets saturated with sensory receptors, Bach-y-Rita deduced that the skin could seamlessly substitute for the eye, but for the brain to translate tactile vibrations into three-dimensional visual imagery, it had to learn an entirely new language. The tactile cortex had to adapt to visual signals. This profound adaptability meant the brain possessed the power to radically reorganize its own sensory perceptual architecture. If the brain could restructure itself to this degree, the prevailing scientific dogma of the era, localizationism, could not possibly be entirely correct. Localizationism, the belief that every mental function is hardwired to a specific, unchangeable geographic location in the brain had ruled neuroscience since 1861. That year, the French surgeon Paul Broca discovered that patients who had lost the ability to speak shared damage in a specific region of the left frontal lobe. Soon after, the physician Carl Wernicke linked the inability to comprehend language to another distinct brain region. These brilliant discoveries calcified into an unbending rule: one function, one location. The brain was viewed as a glorious but fixed machine. If a biological component broke, the function it performed was lost forever. This rigid paradigm initiated a dark age for the concept of brain plasticity. Inconvenient anomalies were swept under the rug. When 19th century researchers found that children could still learn to speak even if the left hemisphere wasted away, or that young animals could move after their motor cortices were surgically removed, the scientific establishment simply ignored the evidence. Bach-y-Rita's own departure from this dogma began in Germany in the early 1960s. While studying the visual processing center of a cat's brain, his research team expected their monitoring electrodes to spike only when the feline was shown an image. They did, but the visual neurons also fired when the cat's paw was stroked or when it heard a sharp sound. Bach-y-Rita realized that the brain's regions were inherently polysensory, naturally capable of processing multiple types of sensory input. This polysensory capability exists because all sense organs, whether eyes, ears, or skin, perform the exact same basic function. They translate environmental energy into electrical impulses. Inside the dark, silent vault of the skull, there are no sounds, colors, or physical textures, only the universal language of electrical spikes. Furthermore, as other researchers were discovering, the cellular architecture of the visual, auditory, and sensory cortices is remarkably homogeneous. Given this uniform structure and universal electrical language, Bach-y-Rita concluded that any region of the cortex should be capable of processing whatever data stream was routed into it. Our cerebral compartments were not nearly as specialized as the textbooks claimed. Emboldened by his tactile vision machine, which proved that the brain could adapt to artificial sensory streams, Bach-y-Rita mounted a lonely protest against the localizationist empire. The backlash was swift and severe. Respected scientific journals rejected his papers a half-dozen times, not because his data was flawed, but because he dared to include the controversial word plasticity in the title. His own mentor, the Nobel laureate Ragnar Granit, privately urged him to abandon his tactile vision device, dismissing it as a mere adult toy. But Bach-y-Rita was undeterred, propelled by a profound personal experience that had forever altered his understanding of the brain's regenerative power. The origin of his belief in rehabilitation lay in the story of his own father, Pedro Bach-y-Rita, a Catalan poet and scholar. In 1959, at the age of 65, Pedro suffered a massive stroke that left him paralyzed on one side of his body, his face slack, and his speech obliterated. The American medical establishment offered a bleak prognosis, declaring his condition permanent and recommending institutionalization. Instead, Paul's brother George, then a medical student in Mexico, brought their paralyzed father south and initiated a grueling, unconventional rehabilitation program. Ignorant of the pessimistic rules of standard physical therapy, George decided that for his father to walk again, he must first relearn to crawl. Supporting Pedro against a wall, George forced him to laboriously drag himself across the floor. They turned every mundane daily activity into a relentless exercise. To recover hand coordination, Pedro was tasked with washing pots, grinding his weak, spastic hand in circles against the metal for hours. The regime was agonizing, but the results defied medical logic. Slowly, Pedro transitioned from crawling to standing and then to walking. He regained his speech and taught himself to type again by dropping his entire arm onto the typewriter keys, gradually refining the movement down to his fingertips. Within a year, the incurable stroke victim returned to full-time teaching in New York, lived an active life, remarried, and spent his final years hiking in the Andes before passing away from a heart attack at the age of 72. The true magnitude of Pedro's recovery remained a mystery until his autopsy. When Paul was called to view the preserved slices of his father's brain, he was stunned. The stroke had not been a minor, transient event. It had caused a catastrophic, permanent lesion. 97% of the nerves connecting his cerebral cortex to his spine had been annihilated. Yet, Pedro had recovered. For Paul, the implications were undeniable. His father's brain had completely reorganized itself, forging entirely new pathways to bypass the massive damage. This revelation prompted Paul Bach-y-Rita to shift his career into rehabilitation medicine. He realized that the standard medical practice of halting therapy when a patient plateaued was a tragic mistake. Plateaus were merely consolidation phases in a continuous plasticity-driven learning cycle. He began treating severe facial paralysis by surgically routing tongue nerves to facial muscles, then training the brain to express emotion through a nerve originally designed for eating. He developed electronic sensory gloves to grant astronauts finer touch in space and to restore sensation to leprosy patients, and he continued to shrink his tactile vision machine down to the small tongue display unit that would eventually give Cheryl Schiltz her life back. Decades after Bach-y-Rita began his crusade, his theories were vindicated by astonishing laboratory experiments. In a landmark study, neuroscientist Mriganka Sur surgically severed the optic nerves of newborn ferrets and reattached them to the animal's auditory cortices. The results were breathtaking. The ferrets learned to see using the hearing centers of their brains. The auditory cortex had plastically reorganized itself to process visual space, proving definitively that brain tissue is inherently flexible and opportunistic. The miraculous recovery of Cheryl's balance, the sight of blind men perceiving faces through vibrations on their tongues, and the ferrets seeing with their auditory centers are not anomalies of nature. They are profound demonstrations of a fundamental biological truth. The sensory cortex is fiercely adaptable. We are, as cognitive scientists now observe, natural-born cyborgs, inherently capable of integrating with tools, computers, and artificial sensors because our neural architecture is designed to constantly re-evaluate and restructure itself. Nature has endowed us with an organ that survives a chaotic, unpredictable world by possessing the ultimate survival mechanism, the ability to change itself. Chapter 2. Building herself a better brain. A woman labeled retarded discovers how to heal herself. The people who make monumental discoveries about the brain are rarely the ones suffering from its defects. Usually, it is a brilliant scientist observing a damaged patient, but there are exceptions. Barbara Arrowsmith Young is one of them, a woman who fundamentally altered our understanding of the mind by healing her own. To understand Barbara as a young girl is to understand the word asymmetry. Born in Toronto in the early 1950s and raised in Peterborough, Ontario, she possessed a mind that was a chaotic landscape of absolute brilliance and profound retardation. Her auditory and visual memory tested in the 99th percentile. Her frontal lobes drove her with a dogged, unrelenting determination. Yet, alongside these gifts were devastating voids. This asymmetry was written into her very flesh. Her right leg was longer than her left, shifting her pelvis, her spine twisted with scoliosis. Her right arm would not straighten, her right side was visibly larger, and her left eye drifted, less alert than its partner. But the physical disarray was nothing compared to the neurological confusion within. She was afflicted with an agonizing array of learning disabilities. A dysfunction in Broca's area made pronouncing words a struggle. She entirely lacked spatial reasoning, the invisible, unconscious map we all use to navigate our bodies through the physical world. At 3 years old, playing a game of Matador in her driveway, she charged an incoming car, mistakenly believing she could easily judge the space and swerve. She misjudged completely, ripping her head open in a collision so severe her mother doubted she would survive the year. Without a spatial map, she could not organize her environment. Out of sight was literally out of mind. To keep track of her possessions, she became a pile person, leaving closet doors wide open and stacking her belongings in plain view. Outdoors, she was perpetually lost. She also suffered from a kinesthetic deficit. She could not feel where her left-sided limbs were in space. She was famously clumsy, tripping over nothing, endlessly spilling juice from her left hand, her left side forever covered in bruises. Her visual span was so narrow she could only take in a few letters of a page at a time. Yet her most debilitating affliction lay in the profound inability to understand the relationships between symbols. Grammar, Mathematical concepts, logic, and the fundamental rules of cause and effect were alien languages. She could not comprehend the difference between the father's brother and the brother's father. A double negative was an impenetrable cipher. She could not read a clock because the relationship between the minute and hour hands made no sense. She could not tell left from right. The world was a mirror maze. She reversed letters, reading was as saw, and wrote from right to left. Because she was right-handed, this mirror writing meant her hand smeared ink across every page she touched. Her teachers, ignorant of her inner turmoil, simply deemed her obstreperous. The cost of her dyslexia was sometimes physical. Misreading a label her brothers had written on an old nose drops bottle, she once unwittingly poured sulfuric acid into her sinuses, too deeply ashamed of her constant blunders to confess the agonizing mishap to her mother. Because she could not grasp cause and effect, her social behavior was erratic. She could not connect an action to its consequence. Math was an exercise in pure, uncomprehending rote memory. She could memorize that 5 times 5 was 25, but she could never understand why. To survive, she found a seat in the classroom where the sunlight made the paper of her flashcards translucent, allowing her to cheat by reading the answers backward. She lived entirely in lag time. Nothing in her reality made sense as it occurred. She survived high school by memorizing pages of facts during lunch, praying her exams would test memory rather than conceptual relationships. To participate in human interaction, she had to mentally replay simple conversations and movie dialogue 20 times over, painstakingly deciphering the fragments long after the moment had passed. She was plagued by chronic, terrifying doubt. The world felt no more solid than cotton candy. She lived in a perpetual fog, secretly fearing she was going insane. In the Peterborough of the 1950s, there were no specialists or special education classes. You were either bright, average, slow, or retarded. Barbara's family was highly driven. Her father an inventor with dozens of patents. Her mother a woman who believed every problem could simply be fixed with enough willpower. The pressure to succeed was immense, and the shame of failure was born in absolute silence. Hoping to unravel the mystery of her own mind, she studied child development at university. Her remarkable compensatory ability to read nonverbal cues earned her a spot in graduate school at the Ontario Institute for Studies in Education. There, she survived on 4 hours of sleep, reading single research papers 20 times over just to grasp a fleeting sense of their meaning. It was there she met Joshua Cohen, another gifted but dyslexic student who ran a clinic based on the accepted dogma of the era, compensation. The scientific consensus held that brain damage was permanent. If a function was broken, you worked around it. You gave a slow reader an audio tape. You gave a slow writer more time. But Barbara's thesis proved that these compensations were not fundamentally helping the children in the clinic, and they could not help her, for her deficits were so vast she had barely enough healthy functions to compensate for the broken ones. Exhausted and profoundly depressed, she stood on subway platforms, calculating the best spot to jump from for maximum fatal impact. Salvation arrived in the form of a book by the Russian neuropsychologist Alexander Luria. Joshua had handed her Luria's work detailing the case study of Comrade Lyova Zazetsky, a young Russian lieutenant who had survived a horrific bullet wound to the brain during the Battle of Smolensk. The shrapnel had lodged deep in his left hemisphere, perfectly destroying the junction where the temporal, occipital, and parietal lobes meet, the exact neurological crossroads where perceptions are integrated and symbols are related. Zazetsky's diary described a life of terrifying fragmentation. He could not understand prepositions, could not grasp cause and effect, and could not understand a whole sentence. He lived in a haze of isolated images. Reading the soldier's tragic diary, Barbara experienced a revelation. He is describing my life. For the first time, her torment had a physical address. She knew exactly which region of her brain was failing. But Luria offered no cure. It was a second paper, written by Mark Rosenzweig at the University of California, Berkeley, that provided the spark of life. Rosenzweig had discovered that rats raised in highly stimulating environments actually developed heavier brains, with more neurotransmitters and better blood supply. The brain, Rosenzweig proved, could change its physical structure through activity. If the brain could physically change, Barbara reasoned, then compensation was not the only answer. The brain could be rebuilt. She retreated into isolation and began a grueling regime of mental exertion targeting her most catastrophic weakness, the inability to relate symbols. She created hundreds of flashcards featuring complex clock faces. She shuffled them, drew a card, attempted to read the time, checked the answer on the back, and relentlessly moved to the next. When she failed, she would sit for hours with a physical clock, painstakingly moving the hands, forcing her brain to comprehend the relationship between the hour and the minute. She worked for weeks, driving herself to the brink of total mental exhaustion. But slowly, the fog began to lift. When she finally mastered the hours and minutes, she added a hand for seconds, and then another for fractions of a second. The transformation was miraculous. Not only could she read clocks faster than anyone she knew, but the neurological pathway she was hammering into existence began to spill over into her daily life. For the first time, she could comprehend grammar, logic, and mathematics. For the first time, she could understand what people were saying while they were saying it. She had dragged her mind into real time. Spurred by this triumph, she developed exhaustive, targeted exercises for her spatial, kinesthetic, and visual deficits, eventually bringing her functioning up to an average, normal level. In 1980, she and Joshua opened the Arrowsmith School in Toronto, discarding the crutch of compensation to focus entirely on neuroplastic rehabilitation. Students at Arrowsmith sit in quiet, intense concentration, systematically rebuilding the weakened pillars of their cognition. Children who cannot grasp symbols sit before computers, reading mind-numbingly complex 10-handed clocks, calculating months, years, and seconds in a fraction of a moment. Other children, sporting pirate-like eye patches to force visual input into a specific, weakened hemisphere, diligently trace intricate Urdu and Persian characters to rebuild their visual memory. Barbara recognized that reading, writing, and speaking are not isolated skills but symphonies of complex movements orchestrated by the left premotor cortex. A weakness in this area causes a child to write in jerky, isolated print, to skip words while reading, and to speak in halting, stuttering fragments, overwhelmed by the sheer neurological demand of translating thought into sequential muscular action. By forcing these children to trace incredibly complex lines and squiggles, the school physically strengthens the premotor cortex. The results are life-altering. Children who arrived reading at a first-grade level soon read for pleasure, their speech flowing naturally, their writing smoothed into cursive grace. There are exercises to rebuild auditory memory through the rote memorization of poetry, curing the children who are unfairly labeled lazy simply because their brains cannot hold more than a few words in their minds at a time. There are exercises for the socially clumsy, targeting the specific brain regions required to read nonverbal cues. There are regimens for impulsive children, strengthening the frontal lobes that govern planning, strategy, and foresight. Barbara's work sheds a revealing light on the history of education itself. For centuries, classical education relied on rote memorization of long poetry and fanatical attention to cursive handwriting. Though discarded in the 1960s as rigid and irrelevant, these very practices were, in fact, rigorous neurological exercises that strengthened the auditory memory and the premotor cortex, giving earlier generations a capacity for eloquence and sustained attention that is noticeably fading in the modern era. We have traded the demanding, brain-building drills of the past for the effortless, visual compensation of the digital presentation. The brain is a living, breathing organ, subject to the merciless biological law of use it or lose it. In adolescence, the brain undergoes a massive pruning process, indiscriminately killing off neurons and synaptic connections that have not been firmly established through use. By identifying and aggressively exercising weak cognitive functions in childhood, before this pruning occurs, we can literally alter a child's destiny, saving them from the agonizing self-doubt of the learning disabled label. Yet, this neuroplastic potential does not vanish with youth. Post-mortem examinations of human brains confirm that education and mental exercise physically increase the number of branches among neurons, driving the cells further apart, and increasing the overall volume and thickness of the cerebral cortex. The notion that the brain is a muscle that grows with use is not a poetic metaphor, it is an anatomical fact. Today, Barbara Arrowsmith Young is a sharp, articulate, and deeply empathetic master of multiple skills. The chaotic asymmetry that once defined her existence is gone. Her journey from the brink of despair to the forefront of neuroplastic rehabilitation stands as a profound testament. We are not merely the prisoners of our biological inheritance. We possess the power to build ourselves a better brain. Chapter 3. Redesigning the Brain. A scientist changes brains to sharpen perception and memory, increase speed of thought, and heal learning problems. Tracking down Michael Merzenich requires a level of persistence that perfectly mirrors the scientist's own relentless drive. Regarded by his peers as the world's preeminent researcher on brain plasticity, Merzenich possesses an insatiable curiosity that has pushed the boundaries of neuroscience for decades. Meeting him at his tranquil California retreat, one immediately senses the contrast between the peaceful, sun-drenched surroundings and his fiercely active, churning mind. Merzenich's central thesis is both radical and profoundly hopeful. The human brain is not a rigid vessel with fixed capacities for memory and processing speed, but rather a dynamic, living entity that constantly redesigns its own circuitry. By applying the laws of neuroplasticity, he argues, we can sharpen our perception, accelerate our cognitive speed, and even reverse severe learning deficits. To appreciate the magnitude of Merzenich's discoveries, one must first understand the scientific dogma he sought to overturn. For much of the 20th century, the field of neurology was dominated by the concept of fixed brain maps. In the 1930s, the pioneering neurosurgeon Wilder Penfield demonstrated that the brain contains topographical maps of the body. By applying a delicate electrical probe to the exposed cortex of conscious patients, Penfield could trigger a sensation in a hand or cause a specific muscle to twitch, effectively proving that specific physical regions correspond to precise cortical locations. The prevailing interpretation of Penfield's brilliant cartography, however, crystallized into a rigid localizationist doctrine. Scientists concluded that these maps were universally identical and unalterable from birth to death. The brain was viewed as a sophisticated, pre-programmed machine. If a biological component broke, the function it housed was permanently lost. Merzenich's journey began with the advent of microelectrodes, tools sensitive enough to detect the firing of a single neuron. While a young researcher at Johns Hopkins University, under the guidance of Vernon Mountcastle, Merzenich utilized this microscopic precision to listen in on the brain's internal communication. Around the same time, David Hubel and Torsten Wiesel made their Nobel Prize-winning discovery regarding the critical period. They demonstrated that if a newborn kitten was deprived of visual stimulation in one eye, the brain map corresponding to that eye failed to develop, and the neural territory was usurped by the functioning eye. This proved that the infant brain was plastic, but the scientific establishment firmly maintained that this malleability vanished once the critical period of childhood closed. The adult brain remained, in their eyes, permanently hardwired. Merzenich's initial encounter with adult neuroplasticity was entirely serendipitous. In 1968, alongside colleagues in Wisconsin, he severed a peripheral nerve in a monkey's hand and meticulously sutured it back together. They anticipated that as the nerve regenerated, the axonal wires would cross unpredictably, leading to a chaotic and scrambled brain map. Instead, months later, micromapping revealed a near-normal topographical map. The brain had somehow recognized the distorted incoming signals and systematically reordered its own structure to make sense of them. This revelation shook Merzenich deeply. If the adult brain could actively reorganize its sensory map, the concept of a static, hardwired machine was fundamentally flawed. He scoured historical literature and found forgotten experiments by figures like Carl Lashley, who had hinted at shifting motor maps decades earlier. Yet, when Merzenich attempted to publish his findings with the implication that the adult cortex was plastic, he met intense resistance. The academic environment was deeply hostile to any challenge against the established localizationist view, forcing him to momentarily temper his claims in print to appease his superiors. Unrelenting, Merzenich eventually established his own laboratory in San Francisco and embarked on a series of elegant experiments designed to definitively prove adult neuroplasticity. His early work on the cochlear implant provided a major breakthrough. Critics had argued that the complex auditory cortex could never decode the simplified electrical signals emitted by an artificial device. Merzenich proved them wrong, demonstrating that the auditory maps could adapt to interpret artificial inputs, giving the deaf the ability to hear and laying the foundation for modern cochlear technology. His most undeniable proof of mapping plasticity came from a collaboration with John Cass. In a remarkably simple yet profound experiment, they severed the median nerve of an adult monkey's hand, entirely cutting off sensory input to a specific sector of the brain map. Months later, they mapped the brain again. The once silent region had not remained dormant. Instead, the brain maps corresponding to the adjacent, healthy nerves had dramatically expanded, colonizing the abandoned neural real estate. This experiment vividly illustrated the principle of competitive plasticity. Neural pathways are locked in a relentless, silent battle for cortical territory. The biological law of use it or lose it governs the brain's geography. If a mental or physical skill is neglected, its corresponding brain map is swiftly overtaken by functions that are actively utilized. This mechanism explains the difficulty adults face when trying to eradicate bad habits or acquire a second language. A deeply entrenched habit or a native tongue has already established a massive, highly competitive neural footprint, making it incredibly difficult for new, weaker pathways to gain a foothold. To unravel exactly how these maps form and alter their borders, Merzenich expanded upon the theories of the Canadian psychologist Donald O. Hebb. Hebb had proposed that learning physically links neurons. This concept, often summarized as neurons that fire together, wire together, became the cornerstone of Merzenich's subsequent work. In a striking demonstration of this principle, Merzenich surgically fused two of a monkey's fingers so they moved simultaneously. After months of synchronized use, the brain maps for the two distinct digits merged into a single, unified map. When the fingers were later separated, allowing independent movement, the brain map divided back into two distinct zones. This proved that the timing of sensory input dictates the brain's organization. We develop an orderly topographical map of our hand because we use our fingers in predictable, sequential patterns, wrapping the thumb, then the index finger, then the middle finger around an object. The synchronized arrival of these sensory signals binds their neural representations closely together in the physical tissue of the brain. Merzenich, working alongside Bill Jenkins, then explored how active learning refines these maps. They trained monkeys to lightly press a spinning disc, demanding intense concentration and precise timing for a reward. Over thousands of trials, the brain map for the engaged fingertip grew significantly. More importantly, the individual neurons within the map became exceptionally efficient, requiring fewer cells to perform the task and responding with greater speed and clarity. This optimization process demonstrated that the very speed of our thought is plastic. As we practice a skill, the involved neurons fire more rapidly and synchronize their signals, transmitting powerful, sharp impulses that cut through the brain's background noise. Faster neurons equate directly to faster thinking, a critical component of human intelligence. However, Merzenich noted a critical caveat. This enduring structural change only occurs when the subject pays absolute, undivided attention. Mindless, automatic repetition does not forge lasting neuroplastic alterations. Armed with the knowledge that focused training could physically enhance neural efficiency, Merzenich turned his attention to human learning disabilities. He joined forces with Paula Talal, a researcher investigating children who struggled profoundly with reading, writing, and language comprehension. Talal had discovered that these children were unable to process the fast parts of speech, the rapid, fleeting consonant sounds that anchor spoken language. Merzenich hypothesized that the auditory neurons in these children were sluggish. Because their neural firing rate was too slow, successive sounds blurred together, resulting in a degraded, muddy signal that crippled all subsequent language processing. Together, they developed Fast for Word, a suite of cognitive training programs disguised as children's computer games. The strategy was pure neuroplastic engineering. The programs initially slowed down the fast components of speech, allowing the children's sluggish auditory cortex to clearly register the sounds. As the children accurately identified the phonemes, the software rewarded them, triggering the release of dopamine and acetylcholine, neurotransmitters essential for consolidating new neural connections. Gradually, the games increased the speed of the audio, forcing the brain to adapt to faster processing times. The results were unprecedented. Children who had languished in special education classes for years experienced massive leaps in language comprehension in a matter of weeks. As their auditory processing accelerated and sharpened, the benefits cascaded through their cognition. Handwriting smoothed out, attention spans lengthened, and overall intelligence scores rose. By fundamentally repairing the auditory signal at its neurological source, Merzenich had proven that developmental deficits were not permanent hardware failures, but rather modifiable processing delays. The success of Fast Forward yielded an unexpected observation. A subset of children diagnosed with autism experienced significant improvements in their social connectedness and behavioral symptoms after completing the auditory training. This prompted Merzenich to investigate the neuroplastic origins of autism itself. Autism represents a catastrophic developmental failure characterized by social isolation, sensory hypersensitivity, and a profound inability to process a chaotic environment. Merzenich theorized that the disorder stems from an anomaly during the critical period of infancy. During this window, a baby's brain maps are highly impressionable, rough drafts. Normal exposure to the environment causes the release of brain-derived neurotrophic factor, BDNF, a chemical that solidifies these connections, turning the rough drafts into sharply differentiated maps. Once the maps are refined, BDNF helps close the critical period, shifting the brain into a more stable adult state. In children with a genetic predisposition to autism, Merzenich suspected that an environmental trigger, perhaps the continuous, indiscriminate hum of modern electronic white noise, overexcites the developing auditory system. This massive stimulation causes a premature and overwhelming release of BDNF. Instead of selectively reinforcing distinct pathways, the chemical indiscriminately locks in the entire undifferentiated rough draft of the cortex and prematurely slams the critical period shut. The child is left with a highly excitable, noisy brain where a single sound can trigger a cascade of indiscriminate neural firing. This lack of cortical differentiation explains the sensory overload, the high incidence of epilepsy, and the autistic child's desperate need to withdraw from a booming, buzzing world. Merzenich successfully replicated this effect in animal models, demonstrating that rat pups exposed to continuous white noise during their critical period developed identical cortical abnormalities. To prove that the critical period could be reopened, Merzenich and his colleague Michael Kilgard conducted a groundbreaking experiment. By artificially stimulating the nucleus basalis, the brain region responsible for focusing attention and maintaining the plastic state of the critical period. In adult rats, they allowed the animals to effortlessly develop new brain maps for sound frequencies. This incredible achievement opened up the theoretical possibility of high-speed learning in adulthood, offering hope for rapid rehabilitation in brain-injured patients and effortless skill acquisition later in life. Merzenich's conviction that the brain's machinery can be continually upgraded inevitably led him to confront the cognitive decline associated with aging. Mainstream medicine largely views the fading memory and slowing cognition of the elderly as an inevitable consequence of physical neural decay, treatable only by drugs that temporarily boost failing neurotransmitter levels. Merzenich vigorously rejects this pessimistic paradigm. He argues that cognitive decline is primarily a disease of disuse. In youth, we are constantly engaged in acquiring completely new skills, a process that demands intense focus and continuously activates the nucleus basalis. But as we transition into middle and old age, we largely abandon the rigors of novel learning. We settle into the comfortable execution of already mastered skills. Without the strenuous demand of focused learning, the nucleus basalis atrophies. The production of essential neurotransmitters diminishes, and the brain's maps lose their crisp definition, devolving into fuzzy engrams. Memories become cloudy because the neural signals used to record them have become weak and imprecise. To combat this, Merzenich established posit science to design brain exercises specifically engineered to rejuvenate the aging cortex. These exercises do not rely on simple memorization tricks. Instead, they force older adults to systematically retrain their sensory processing. By intensely focusing on distinguishing subtle, rapid changes in sound, the elderly participants force their neurons to fire faster and more clearly, stimulating the production of dopamine and acetylcholine. Clinical trials have yielded staggering results, demonstrating that focused, plasticity-based training can effectively turn back the cognitive clock by decades, restoring the memory, processing speed, and problem-solving abilities of an octogenarian to those of a middle-aged adult. Merzenich's vision challenges the very foundation of human limitation. He posits that if we provide the brain with the correct stimuli, delivered with precise timing and demanded with rigorous attention, the adult brain can undergo transformations every bit as profound as those seen in a newborn. The brain is not a static repository of fading abilities, but a continuously evolving architecture, shaped endlessly by the world it interacts with and the mental effort we choose to exert. Chapter 4. Acquiring Tastes and Loves. What neuroplasticity teaches us about sexual attraction and love. A young, handsome man, known in clinical records simply as A, sought psychiatric help because he was engulfed by a profound depression. He had recently escaped a relationship with a striking woman who was not only already attached to another man but who actively encouraged A to abuse her. She drew him into dark scenarios, asking him to treat her like a prostitute and to enact violent, dominating fantasies. A broke off the relationship when he realized, to his horror, that he was beginning to desire exactly what she was asking for. His romantic history was a graveyard of similar entanglements. He was chronically drawn to women who were unavailable, emotionally volatile, and remarkably cruel. Kind, stable women bored him entirely. He viewed uncomplicated affection as a defect. The blueprint for this destructive appetite had been drawn in his childhood. His mother was a severe alcoholic, prone to sudden rages and desperate neediness. A recalled agonizing scenes of her violence, such as burning his stepbrother's fingers for playing with matches. Yet she was also inappropriately seductive, parading in sheer nightgowns and speaking to him as though he were an adult lover. Young A lived in a state of perpetual tension, stifling his own rage while trying to calm his mother's storms. Intimacy for him became synonymous with danger and boundary crossing. By the time he reached adulthood, his erotic tastes were rigidly locked onto women who promised to replicate the chaotic, dangerous environment of his youth. When we observe the sheer variety of human sexual behavior, we encounter a level of plasticity unseen in any other species. In the animal kingdom, sexual instinct is a biological imperative, a rigid behavioral loop designed strictly for reproduction. Human sexuality, however, has broken free from this singular biological mandate. We exhibit an astonishing array of preferences, fetishes, and romantic types. A person's sexual tastes can shift dramatically over a lifetime, adopting new attractions and discarding old ones. Some individuals find themselves aroused not by other humans but by inanimate objects, while others require complex, highly orchestrated scripts of dominance and submission to feel any desire at all. This vast spectrum of desire points to a profound neurological truth. The human libido is not a hardwired, invariable machine. Research confirms that plasticity is not confined to the cerebral cortex, the thinking, processing part of the brain. The hypothalamus, which regulates our deepest animal instincts, and the amygdala, the emotional epicenter of the mind, are deeply plastic. The rules of neuroplasticity apply to our most primitive urges, just as they do to our capacity for language or mathematics. Sigmund Freud was among the first to recognize the fundamental malleability of human desire, noting that the sexual instinct was remarkable for its capacity to alter its aims and objects. Freud introduced the concept that our adult capacity for love and lust unfolds through critical periods in early childhood. During these brief, intensely formative windows, a child's brain maps are shaped by their primary caregivers. If a parent is warm and reliable, the child's neural networks wire those traits into their definition of love. If a parent is distant, erratic, or abusive, those painful dynamics become neurologically entwined with the child's developing sense of attachment. We can observe the lingering neural echoes of these early critical periods in everyday romantic behavior. When adult lovers retreat into the privacy of the bedroom, they frequently use terms of endearment like baby or sweetheart, adopting a tender, cooing tone. This baby talk is not merely an affectation, it is a neurological regression. It reactivates the ancient neural pathways laid down during the first months of life, a phase defined by the warmth, feeding, and absolute security provided by a mother. Conversely, the phenomenon of talking dirty during intimacy reflects a regression to a slightly later developmental stage, when a child first becomes aware of the proximity between the organs of elimination and the organs of reproduction. By revisiting these early primal states within the safe bounds of adult intimacy, individuals utilize their brain's plasticity to heighten emotional and physical connection. The realization that our sexual desires are molded during critical periods challenges the widespread assumption that physical attraction is purely a matter of evolutionary biology, that we are simply drawn to signs of fertility and strength. While biology plays a role, our deepest desires are often acquired tastes. An infant does not need to learn to enjoy the taste of milk. It is an innate preference. But the appreciation for bitter coffees, pungent cheeses, or dry wines must be learned through repeated exposure until the brain rewires itself to perceive the initially unpleasant stimulus as deeply satisfying. Once a taste is acquired and wired into our neural architecture, it feels entirely natural. Nowhere is the phenomenon of acquired sexual taste more starkly visible than in the modern epidemic of internet pornography. Pornography is often defended as a simple release of pent-up natural instincts. But if pornography merely satisfied a hardwired biological urge, its content would remain static. Instead, the imagery that viewers consume has grown exponentially more extreme. What was considered hardcore decades ago is now easily accessible softcore. The modern digital landscape is increasingly dominated by aggressive, specialized, and degrading scripts. High-speed internet pornography provides the perfect neurological environment for inducing massive plastic change in the adult brain. It demands intense focus and offers endless repetition. Most crucially, it hijacks the brain's dopamine system. Dopamine is the neurotransmitter of reward and anticipation. It gives us the thrilling surge of energy when we pursue a goal. When an individual views pornography and achieves sexual release, the brain is flooded with a massive chemical reward. Because neurons that fire together wire together, this dopamine surge physically consolidates the neural connections associated with the specific images on the screen. As viewers repeatedly subject their brains to this intense stimulation, they develop tolerance. The neural receptors become overwhelmed and down-regulate, meaning the viewer requires harder, more shocking material to achieve the same chemical high. Furthermore, they develop sensitization, a state where they experience intense, compulsive cravings for the imagery, even if they no longer truly enjoy it. This separation of wanting from liking is the hallmark of neurological addiction. The brain's appetitive pleasure system, driven by dopamine, becomes hyperactivated, while the consummatory pleasure system, driven by the peaceful release of endorphins, is sidelined. The result is a phenomenon where ordinary, well-adjusted individuals find their sexual tastes radically altered. Men who have wired their brains to respond to aggressive, highly specific digital scripts often find themselves unable to respond to their real-world partners. The gentle, unscripted reality of human intimacy cannot compete with the massive dopamine spikes promised by the glowing screen. Their brains have been meticulously retrained, their libidos rebuilt into what can be described as a neosexuality, assembled from dormant psychological quirks, unmasked and fused together by endless digital surfing. Yet, just as the brain can wire itself into destructive appetites, it also possesses a profound capacity for unlearning and renewal, a process most vividly experienced when we fall in love. Romantic love triggers a state of neurological euphoria that rivals any chemical narcotic. When we fall in love, the pleasure centers of the brain fire with intense ease. This creates a state of globalization, where the lover is filled with optimistic anticipation and finds delight in the entire world. In this highly plastic, dopamine-drenched state, our aesthetic tastes can be entirely rewritten. As the 19th century writer Stendhal observed, a man deeply in love might find a physical flaw in his mistress, such as a pockmark, intensely arousing because that flaw is repeatedly presented alongside exquisite emotional and physical pleasure. The brain wires the visual reality of the flaw directly into the pleasure centers, transforming objective ugliness into subjective beauty. But the neurological demands of love go far beyond the initial euphoric high. To forge a lasting bond with another human being, the brain must undergo a massive period of unlearning. Millions of pre-existing neural networks dedicated to solitary routines, selfish intentions, and past attachments must be dismantled to make room for the new partner. This profound neurological reorganization is facilitated by a neuromodulator called oxytocin. Often referred to as the commitment chemical, oxytocin is released during deep, intimate contact, orgasm, and, in women, during childbirth and nursing. Unlike dopamine, which provokes excitement and craving, oxytocin induces a warm, trusting calm. More importantly, oxytocin acts as an amnestic. It melts down the rigid neural pathways of existing behaviors, rendering the brain exceptionally pliant. It does not magically teach us how to be a good partner or a devoted parent. Rather, it dissolves our deeply ingrained self-centeredness, providing the neurological opportunity to learn entirely new ways of cooperating and nurturing. This requirement for unlearning also explains the agonizing physical and mental pain of a broken heart. When we lose a deeply loved partner, we are left with billions of neural connections anticipating their presence. Grief is the arduous piecemeal process of firing up each of those memory networks, confronting the reality of the absence and painstakingly dismantling the connections. It is a massive project of neurological rewiring, and its orders, as Freud noted, cannot be obeyed all at once. Understanding this delicate interplay of learning and unlearning provided the key to rescuing the young man A from his torment. A was caught in a neurological trap. He had fused the concepts of sex and violence so tightly in his mind that he could not experience one without the other. In neuroplastic terms, the brain maps for tenderness and aggression had merged. Just as a musician who practices with poor technique might accidentally fuse the brain maps for two fingers, causing them to move together uncontrollably, A had fused the maps for love and danger. To help him escape this trap, the therapeutic approach focused on redifferentiating these merged maps. Whenever A expressed a feeling of pure, non-sexual tenderness, or whenever he demonstrated healthy, non-sexual assertiveness, his attention was intensely drawn to it. Over time, through relentless focus, he began to physically separate the neural network for intimacy from the neural network for aggression. As these brain maps drifted apart, his compulsion to seek out dangerous women faded. He unlearned the destructive template of his childhood and eventually married a stable, loving woman, proving that even our most deeply entrenched romantic fatalisms can be rewired. There is, however, a dark side to the immense plasticity of our pleasure systems, seen most acutely in the world of severe sexual perversions, such as hardcore masochism. To experience physical agony as sexual ecstasy, the brain must execute an astonishing anatomical feat. It must physically wire the pain pathways directly into the pleasure centers. Psychoanalytic investigations into hardcore sadomasochists have revealed a haunting commonality: a history of severe, terrifying medical illnesses and interventions during early childhood. These individuals were subjected to inescapable pain and confinement during the critical periods of their neurological development. To survive the psychological destruction of absolute helplessness, their developing brains performed a desperate alchemy. They took their inexpressible rage and terror and reworked it in their fantasies, eroticizing their agony so that they could finally claim a measure of control over it. This dark plasticity is exemplified in the life of Bob Flanagan, who became famous as a performance artist and super masochist. Born with cystic fibrosis, a disease that clogs the lungs with thick mucus, Flanagan's early life was a nightmare of suffocation, hospitalizations, and agonizing medical procedures. Infants with the disease were routinely confined to plastic tents and subjected to painful needle insertions. Flanagan's world was defined by the adults who inflicted pain upon him for his own good. As he grew, Flanagan began to actively court pain, suspending himself by belts and piercing his flesh with needles. Eventually, he entered a relationship with a dominant woman to whom he surrendered total control, allowing her to subject him to extreme forms of mutilation and suffocation. His survival strategy was to turn the absolute terror of his disease into a sexual triumph. By willingly submitting to torture, he transformed the shame of his childhood medical vulnerability into a defiant, exhibitionistic pride. Physical pain became indistinguishable from sexual release. Yet the plastic brain's ability to turn agony into ecstasy has limits against the ultimate reality of biology. When Flanagan's cystic fibrosis finally began to claim his life in his early 40s, the elaborate masochistic defense he had spent a lifetime constructing collapsed. Facing the true uncontrollable approach of death, he was no longer the triumphant master of his pain, but a terrified child once more, proving that while neuroplasticity allows us to radically alter our experience of the world, it cannot entirely overwrite our fundamental human fragility. Chapter 5. Midnight Resurrections. Stroke victims. Learn to move and speak again. For centuries, the medical verdict following a massive stroke was as final as it was devastating. When a blood clot or a ruptured vessel starves a section of the brain of oxygen, the neural tissue in that immediate area dies. The functions governed by those deceased cells, whether the ability to lift an arm, articulate a sentence, or take a step, were universally considered lost forever. The prevailing belief was that the brain, functioning as a rigidly hardwired machine, possessed no capacity for biological resurrection. Once the acute phase of spinal shock subsided and standard physical therapy plateaued, patients were routinely instructed to accept their permanent disabilities. They were taught how to navigate the world using only their surviving healthy limbs, effectively abandoning the paralyzed side of their bodies to a state of permanent uselessness. This deeply entrenched pessimism was dismantled by the relentless, often controversial work of a neuroscientist named Edward Taub. Taub recognized a profound flaw in traditional stroke rehabilitation, the phenomenon he termed learned non-use. He theorized that the paralysis observed in many stroke victims and in patients with severe nerve damage was not entirely a permanent physical hardware failure. Instead, a significant portion of their immobility was a highly destructive, learned psychological illusion, reinforced by the plastic nature of the brain itself. Taub's revolutionary insights were born from a series of grueling experiments involving somatic deafferentation. In his laboratory, he surgically severed the sensory nerves extending from one arm of several macaque monkeys. The motor nerves, which carry the brain's commands down to the muscles, were left entirely intact. The monkeys could technically still move their affected arms, but they could no longer feel them. Deprived of all tactile feedback and spatial awareness regarding the limb, the animals simply stopped using it. They carried the deafferented arm in a sling-like posture, relying entirely on their 3 healthy limbs to eat, climb, and survive. The neurological establishment of the time interpreted this as proof that movement was fundamentally impossible without sensory feedback. Taub, however, suspected something far more complex was occurring. He recognized that immediately after nerve injury or a stroke, there is a period of severe physiological shock. During this critical window, any attempt to use the damaged limb results in failure, clumsiness, and frustration. The brain, operating on basic principles of behavioral conditioning, registers this failure as negative reinforcement. Simultaneously, the animal discovers that using its healthy limbs leads to successful, rewarded outcomes. Through this mechanism, the subject actively learns not to use the damaged limb. Because the brain operates strictly on a use-it-or-lose-it economy, this cessation of movement triggers a catastrophic neurological retreat. The cortical maps corresponding to the neglected arm begin to shrink rapidly. As the neural territory diminishes, the ability to move the arm becomes genuinely more difficult, feeding a vicious, self-perpetuating downward spiral. The animal believes the arm is paralyzed, and through lack of use, the brain physically erases the arm from its functional inventory. To break this cycle, Taub devised a radically simple intervention. He took the deferented monkeys and placed their single healthy arm in a restrictive sling, eliminating their ability to compensate. Then, he placed food just out of reach, forcing them to rely on the useless, sensationless arm to feed themselves. The results shattered prevailing dogmas. Forced by absolute necessity and extreme motivation, the monkeys began to use their deferented limbs. With relentless, massed practice, they regained the ability to grasp, pull, and feed themselves, proving definitively that the motor programs in the brain were still viable and that sensory feedback was not an absolute prerequisite for movement. Taub's journey to translate this discovery to human stroke patients was violently derailed in the early 1980s. A young animal rights activist named Alex Pacheco infiltrated Taub's Silver Spring laboratory, covertly gathering photographs and staging the facility to appear deliberately cruel. Pacheco triggered a massive police raid, leading to the confiscation of the monkeys and the launch of a sensationalized legal crusade against Taub. He became the primary target of the newly formed People for the Ethical Treatment of Animals, PETA. His funding was severed, his laboratory was shuttered, and he was subjected to years of grueling criminal trials. Although he was eventually exonerated by the courts and the scientific community, which found his work mathematically sound and ethically compliant with the standards of the era, his career was stalled for nearly a decade. Ironically, the tragedy of the Silver Spring monkeys ultimately provided some of the most undeniable proof of neuroplasticity in scientific history. Years later, when the surviving monkeys were humanely euthanized due to failing health, a team of independent neuroscientists painstakingly mapped their brains. They discovered an astonishing anatomical reality. The massive section of the sensory cortex that had originally governed the deferented arms had not remained an empty, dormant wasteland. Instead, the brain map for the monkeys' faces had aggressively expanded, migrating nearly 14 millimeters across the cerebral cortex to colonize the abandoned neural territory. This massive structural reorganization proved beyond any doubt that the adult brain is highly opportunistic and capable of reshaping itself over vast distances. Emerging from his legal nightmare, Taub relocated to the University of Alabama at Birmingham and finally turned his attention to human stroke survivors. He developed a protocol called constraint-induced CI movement therapy. The method was the direct human equivalent of his monkey experiments. To treat a patient with a paralyzed left arm, Taub's clinicians would place the patient's healthy right arm in a heavily padded mitt, physically preventing its use for up to 90% of their waking hours. With the compensatory limb neutralized, the patient was subjected to intense, rigorous training for weeks. They were asked to perform seemingly mundane tasks: wiping tables, turning pegs in a board, stacking blocks, and tracing letters. However, CI therapy is not merely mindless repetition. It relies on a meticulous process called shaping. Clinicians break every complex movement down into its smallest component parts. A patient who cannot grasp a cup is first rewarded for simply twitching a finger, then for lifting a wrist, then for extending an arm. The tasks are constantly, incrementally adjusted to remain just at the edge of the patient's capability, ensuring that the brain is perpetually challenged and highly engaged. The story of Michael Bernstein illustrates the profound impact of this approach. Bernstein was a highly successful 54-year-old pediatric eye surgeon when a massive stroke severed the connections in the right hemisphere of his brain. He lost all functional use of his left side. A man who previously possessed the microscopic dexterity required to operate on the delicate muscles of an infant's eye was suddenly reduced to relying entirely on a cane, his left arm hanging limp and useless. Traditional physical therapy yielded virtually no improvement, and he was advised to simply adjust to a life of profound limitation. Refusing to accept this fate, Bernstein entered Taub's CI therapy program. The process was physically exhausting and emotionally agonizing. Stripped of the ability to use his healthy right hand, he was forced to confront the absolute helplessness of his paralyzed side. For days he struggled with agonizing slowness to complete tasks that a toddler could master in seconds. Frustration frequently boiled over into despair, but beneath the surface of his visible struggle, his brain was rapidly rewiring. The intense, focused effort demanded by the shaping exercises triggered a surge of neurotransmitters that began to reactivate dormant neural pathways surrounding the dead stroke lesion. Because he could not fall back on his healthy arm, his brain was forced to forge new connections, routing movement commands through secondary undamaged neural networks. Gradually, the learned non-use was unlearned. Microscopic improvements compounded. A faint twitch evolved into a deliberate grasp. A clumsy drag became a smooth lift. By the end of the therapy, Bernstein had not only regained the ability to feed and dress himself, but his fine motor control had improved so dramatically that he returned to his medical practice. While he could no longer perform delicate surgeries, he reclaimed an independent, highly functional life that traditional neurology had explicitly declared impossible. The success of CI therapy fundamentally altered the landscape of rehabilitation medicine. Brain scans of patients before and after Taub's program reveal undeniable physical changes. The motor maps corresponding to the paralyzed limbs visibly expand. proving that the focused, massed practice actually grows new neural real estate. Taub's clinic subsequently adapted the constraint principle to treat stroke victims suffering from aphasia, the loss of language. By placing patients in environments where they are strictly forbidden from relying on nonverbal gestures, drawing or pointing, and rewarding them only for attempting to articulate words, clinicians force the brain to rebuild its speech centers. Furthermore, Taub extended this neuroplastic salvation to children afflicted with cerebral palsy. These children, suffering from early brain damage, naturally favor their functioning limbs and quickly succumb to the trap of learned non-use. By constraining their good limbs and engaging them in heavily modified play-based shaping exercises, Taub demonstrated that even developing brains deeply scarred by congenital defects could be dramatically rewired. Edward Taub's journey from pariah to pioneer underscores a profound paradigm shift. The brain, even when severely damaged by stroke or trauma, retains a relentless drive to adapt. The tragic permanency of many paralyzing conditions is not always dictated by the initial physical injury, but by our subsequent failure to demand recovery. By physically blocking the easy path of compensation and rigorously demanding the impossible, we can force the nervous system to resurrect functions long thought dead, dragging patients out from the midnight of paralysis and back into the light of motion. Chapter 6. Brain Lock Unlocked. Using plasticity to stop worries, obsessions, compulsions, and bad habits. There is a specific invisible torment in having a mind that refuses to move forward. For individuals suffering from obsessive-compulsive disorder, or OCD, the brain transforms into a tyrant, trapping them in an endless, agonizing loop of dread and repetition. An individual might wash their hands until the skin cracks and bleeds, driven by a terrifying, unyielding conviction that they are contaminated. Another might spend hours repeatedly checking a locked door or a cold stove, entirely paralyzed by the fear that a catastrophic oversight will cause their home to burn down. They logically know their hands are clean, they intellectually understand the door is secured, yet the overwhelming feeling of impending doom simply will not subside. For decades, the psychoanalytic community approached OCD as a dark manifestation of repressed unconscious conflicts. Patients spent years on couches, desperately trying to unearth childhood traumas or hidden aggressive desires that supposedly fueled their compulsions. This approach was not merely ineffective, it was often actively destructive. By continuously focusing attention on the obsessions, the patients were inadvertently strengthening the very neural circuits responsible for their misery. The disorder is not fundamentally a problem of repressed memories. It is a severe malfunction in the brain's physical machinery, a mechanical failure of mental gear shifting. The neuroscientist and psychiatrist Jeffrey Schwartz recognized this mechanical failure by looking deeply into the anatomy of the brain's error detection system. In a healthy nervous system, when a person makes a mistake or senses a potential problem, a specific sequence of neurological events occurs. First, the orbital frontal cortex, a region situated just behind the eyes, detects the discrepancy. It recognizes that something is wrong, for example, a feeling that the hands are dirty. Immediately, it sends a signal to the cingulate gyrus, a deep brain structure that triggers a visceral sense of anxiety or dread. This is the brain's alarm bell, designed to make the person feel uncomfortable enough to take corrective action. Finally, once the hands are washed, a structure situated deep within the brain called the caudate nucleus engages. The caudate acts as an automatic transmission for the mind. It smoothly shifts the brain's gears, turning off the alarm in the cingulate gyrus and allowing the person to move on to the next thought or activity. In a brain afflicted with OCD, this elegant system is catastrophically jammed. The orbital frontal cortex detects a minor issue, and the cingulate gyrus sounds the alarm of anxiety. But the caudate nucleus, the crucial gear shift, is sticky. It completely fails to engage. The person washes their hands, but the gear does not shift. The alarm continues to blare with terrifying intensity. The orbital cortex continues to insist that a mistake has been made. The patient is caught in what Schwartz termed brain lock. The terrified individual performs the compulsive action again and again, desperately hoping to switch off the agonizing alarm, unaware that they are trapped in a biological loop. Crucially, because the brain operates on the unforgiving law of neuroplasticity, where neurons that fire together wire together, every time the patient yields to the compulsion, they make the lock stronger. Washing the hands for the 50th time does not ease the anxiety. It physically reinforces the neural pathway of the obsession, ensuring that the next attack will be even more intense. The compulsion is not a cure for the obsession. It is the very fertilizer that makes it grow. Realizing that traditional talk therapy was useless against this biological lock, Schwartz developed a revolutionary neuroplastic intervention designed to manually force the brain's gears to shift. He understood that he could not stop the orbital cortex from firing or the cingulate gyrus from sounding the alarm. The feeling of dread would happen regardless, but he could teach patients to change how they responded to that dread, thereby rewiring the faulty circuit from the outside in. Schwartz's method demands an extraordinary act of willpower and cognitive separation. When an OCD attack strikes, the patient is trained to immediately relabel the terrifying thought. Instead of thinking, "I am infected with deadly germs," the patient must forcefully tell themselves, "I am experiencing a severe obsessive-compulsive urge." They are taught to reattribute the profound feeling of dread not to reality, but to the physical malfunction in their own biology. They must view the panic as a false signal, a meaningless neurological hiccup originating from a sticky caudate nucleus. Recognizing the false signal, however, is not enough to break the circuit. The true neuroplastic rewiring occurs in the next excruciatingly difficult phase, refocusing. While the alarm bell is still shrieking in their mind, while the terror of the unwashed hands or the unchecked stove is at its absolute peak, the patient must refuse to perform the compulsion. Instead, they must forcefully direct their attention to a completely different, positive and engaging activity. They might work in the garden, play a musical instrument, knit, or vigorously exercise. They must sustain this alternative action for at least 15 minutes, completely ignoring the screaming demands of their own brain. This act of refocusing is the neurological equivalent of manually pushing a stalled car into a new gear. By engaging in a new activity, the patient is forcing a completely different neural network to fire. Simultaneously, by refusing to perform the compulsion, they are starving the old obsessive circuit of the attention it needs to survive. They are utilizing the use it or lose it principle to weaponize their own biology against the disease. They build a new, healthy neural highway, while allowing the deeply entrenched road of the compulsion to slowly turn to dust through neglect. The ultimate validation of this method came from inside the brain itself. Schwartz conducted brain scans on his patients before they began the therapy and compared them to scans taken weeks later. The visual evidence was undeniable. The patients who successfully employed the relabeling and refocusing techniques had fundamentally altered the physical structure of their brains. The intense, hyperactive firing in the orbital cortex and the cingulate gyrus had significantly quieted. The previously sticky caudate nucleus was functioning smoothly. This breakthrough carried implications far beyond the realm of clinical OCD. It provided a stark biological blueprint for how all human habits, both good and bad, are formed and broken. A bad habit is simply a deeply carved neural pathway, reinforced by years of mindless repetition. When a person tries to quit smoking, stop overeating, or break a cycle of chronic worrying, they are fighting against massive, highly efficient brain maps that demand to be utilized. Attempting to break a bad habit simply by telling oneself not to do it is nearly impossible because it keeps the brain's attention focused squarely on the habit itself, inadvertently keeping the neural circuit active. The neuroplastic solution to breaking a destructive cycle is not resistance, but redirection. The individual must acknowledge the urge, accept that it is a biological craving firing in the brain, and immediately pivot their entire focus onto a competing, constructive action. Through disciplined, sustained refocusing, the brain's architecture is slowly but permanently remodeled. The mind, through sheer, focused effort, possesses the profound capability to physically alter the brain, proving that we are not merely the helpless victims of our own automatic biology. Chapter 7. Pain. The dark side of plasticity. When we wish to perfect our senses or learn a new skill, neuroplasticity is a profound blessing. But when this same biological mechanism works in the service of pain, plasticity can become a devastating curse. Our guide to the dark side of plasticity is V.S. Ramachandran, a neurologist and researcher who seems like a proud relic of 19th century science tackling 21st century dilemmas. Born in Madras, India, and educated at Cambridge, Ramachandran is the director of the Center for Brain and Cognition at the University of California, San Diego. He is the Sherlock Holmes of modern neurology, a sleuth who solves mysteries one bizarre case at a time. He maintains a disdain for complicated, fancy equipment and large statistical studies, preferring the elegant simplicity of Victorian-era science. His office is a testament to this, filled with optical stereoscopes, 19th century magnifying glasses, fossils, and the preserved brain of an adolescent. He believes that by paying close attention to neurological oddities and illusions, he can unravel the deepest mysteries of the normal human brain. Using little more than a mirror and a cardboard box, Ramachandran solved a medical mystery that had baffled doctors for centuries, the agony of the phantom limb. There is a whole host of haunting pains that torment human beings for reasons we do not fully understand. Lord Nelson, the British admiral who lost his right arm in an attack in 1797, vividly experienced the presence of his missing limb. He concluded that this phantom arm was direct evidence for the existence of the soul, reasoning that if an arm could survive the annihilation of the flesh, so too must the entire person. During the American Civil War, the physician Silas Weir Mitchell, tending to soldiers whose gangrenous limbs had to be sawed off, noted an epidemic of these sensory ghosts, which he officially named phantom limbs. These phantoms are not merely ethereal memories. They are lively, undeniable entities. Amputees feel their missing arms gesticulating when they talk, waving to friends, or reflexively reaching to break a fall. Tragically, in 95% of amputees, these phantoms give rise to chronic, agonizing pain. For decades, doctors assumed the pain was caused by irritated nerve endings in the stump. They subjected patients to serial amputations, cutting the stump farther and farther back, hoping to sever the source of the agony. But after every surgery, the painful phantom always returned. How, doctors wondered, do you remove a pain in an organ that no longer exists? Ramachandran's breakthrough began when he read about the final experiments on Edward Taub's deafferented monkeys. When the sensory input from the monkey's arms was completely severed, the brain map for the arm did not sit idle. Instead, the adjacent brain map, the one governing the face, migrated and took over the abandoned neural real estate. Ramachandran realized that patients with phantom limbs were exactly like those monkeys. If the face map had invaded the arm map, could it be that when an amputee was touched on the face, he would actually feel the touch in his missing arm? He tested this theory on a young man named Tom Sorensen, who had lost his arm in a terrible automobile accident at the age of 17. Tom was haunted by his phantom limb, particularly by an incessant, maddening itch in his missing hand that he could not scratch. Ramachandran blindfolded Tom and took a simple cotton Q-tip, gently stroking different parts of Tom's upper body. When he touched Tom's cheek, Tom reported feeling the Q-tip on his cheek, but also distinctly on his phantom thumb. When Ramachandran stroked Tom's upper lip, Tom felt it in his phantom index finger. Ramachandran let a drop of warm water slide down Tom's face, and Tom felt the warm trickle sliding down his non-existent arm. The neural maps for Tom's face and hand had completely blurred together. The brain, starving for sensory input after the amputation, had sprouted new connections, inviting neurons from the active facial map to invade the dormant territory of the hand. Finally, after weeks of torment, Tom discovered that he could successfully scratch the agonizing itch in his phantom hand simply by scratching his own cheek. But Ramachandran soon discovered that not all phantoms are so easily appeased. As he interviewed more amputees, he found that about half of them suffered from frozen phantoms. Their missing limbs felt paralyzed, encased in a block of cement, or hanging as a dead, agonizing weight. In the most horrific cases, the trauma of the amputation itself was locked into the phantom. Soldiers whose hands were blown apart by grenades felt the excruciating pain of the explosion playing on an endless loop. Patients whose frostbitten thumbs were removed felt the eternal burning agony of the frostbite. Ramachandran noted a fascinating commonality among the patients with frozen phantoms. They had almost all worn their arms in slings or casts for months prior to the amputation. Because their arms were immobilized, their brain maps had fundamentally learned that the limb could not move. Normally, when the brain's motor center sends a command to the arm to move, the arm's sensory nerves send back a visual and physical confirmation that the movement has occurred, but for the amputee, this feedback loop is shattered. The brain's motor center sends the command to clench the hand. Receiving no confirmation that the hand has clenched, the brain escalates the command. Clench! You are not clenching enough! The brain continuously fires its most extreme motor commands into the void. Because maximum muscle contraction and pain are inextricably linked in the brain's memory, this imaginary clenching triggers intense, blinding pain. The patients literally feel their non-existent fingernails digging into their non-existent palms. If this phantom paralysis and pain were the result of a learned illusion, Ramachandran wondered if he could invent a counter-illusion to help the brain unlearn it. He wanted to find a way to visually trick the brain into believing that the phantom limb was moving, thereby restoring the broken feedback loop and turning off the desperate motor commands. He built a mirror box. It was a simple cardboard box the size of a cake box with the top removed and 2 holes cut in the front. Down the center of the box, he placed a vertical mirror. He tested the device on Philip Martinez, a man who had lost his left arm in a motorcycle crash. The nerves had been ripped directly from Philip's spine, leaving him with a paralyzed, agonizing phantom elbow and arm that drove him to the brink of suicide. Ramachandran instructed Philip to put his good right arm through the right hole and to imagine putting his phantom left arm through the left hole. When Philip looked down into the box, the mirror reflected his good right hand perfectly, but because of the mirror's placement, it looked exactly like his missing left hand had been resurrected. Ramachandran asked him to move his right hand while looking in the mirror. As the reflection moved, Philip gasped. For the first time in years, he not only saw his phantom arm moving, but he physically felt it moving. The intense pain in his elbow vanished. He joyfully declared that his arm felt plugged in again. The visual feedback from the mirror had successfully overridden the desperate, pain-inducing motor commands in his brain. Ramachandran sent Philip home with the box, instructing him to use it for 10 minutes a day. Philip practiced diligently. 4 weeks later, he called Ramachandran with astonishing news. Not only had the pain remained at bay, but the phantom arm itself had completely disappeared. Stripped of the illusions that sustained it, the neural map had dissolved. Ramachandran had successfully performed the first amputation of a phantom limb. The success of the mirror box reveals a profound truth about human biology. Our experience of our own bodies is an illusion. We do not experience our bodies directly. We experience the body image constructed by our brain maps. Ramachandran points out that your own body is a phantom, one constructed purely for the brain's convenience. When a person suffers a back spasm and cries, "My back is killing me," they are biologically incorrect. It is their brain's pain map that is killing them. For centuries, following the logic of the philosopher René Descartes, medicine viewed the brain as a passive recipient of pain. Scientists believed that a pain receptor in the skin acted like a bell rope. Pull the rope, and a bell rings in the brain. The intensity of the pain was assumed to be strictly proportional to the severity of the injury. This mechanistic view was dismantled in 1965 by Ronald Melzack and Patrick Wall, who published the revolutionary gate control theory of pain. They proved that the pain system is not a passive alarm, but a highly active plastic network spread throughout the spinal cord and the brain. When tissue is damaged, the pain signals do not travel freely to the mind. They must first pass through a series of neurological gates. The brain actively evaluates the situation and decides whether to grant the signals permission to enter consciousness. If the brain determines the pain is necessary for survival, it opens the gates, allowing the neurons to fire and the agony to be felt. But the brain can also slam the gates shut, flooding the system with naturally produced endorphins to completely block the pain. This explains why soldiers severely wounded on the battlefield often report feeling no pain whatsoever until they are safely out of the line of fire. The brain closes the gates to keep the soldier's attention absolutely focused on survival. It explains why a sugar pill can act as a powerful analgesic, because the patient's expectation of relief signals the brain to actively turn down its own pain-responsive regions. Pain, Ramachandran concluded, is not a reflexive response to injury. It is the brain's opinion on the organism's state of health, and because the pain system is deeply plastic, this opinion can become horribly distorted. When a person sustains an injury, the brain reflexively commands the surrounding muscles to freeze and guard the wounded area. But in some cases, the plastic brain learns this guarding response too well. The motor command to freeze becomes physically wired directly into the pain system. Long after the original tissue has healed, the simple act of trying to move the limb triggers an explosion of localized agony. This condition, known as reflex sympathetic dystrophy or type 1 chronic pain, leaves patients with limbs that burn with excruciating pain at the lightest touch. Ramachandran theorized that the mirror box could help these patients as well by visually convincing the brain that the limb could move without injury, thus breaking the pathological link between movement and pain. He instructed patients whose arms were immobilized by this condition to place both hands in the mirror box and move their healthy arm while looking at the reflection. For patients who had suffered the condition for a few months, the relief was rapid and permanent. The brain unlearned the pain. However, patients who had suffered the pain for over 2 years did not improve. Their limbs had been immobilized for so long that the motor maps had wasted away due to the merciless law of use it or lose it. They physically could not engage with the mirror therapy. An Australian scientist named G.L. Moseley developed an ingenious solution for these entrenched cases. He reasoned that he could rebuild their withered motor maps using pure imagination. Moseley instructed these patients to sit quietly and vividly imagine moving their painful limbs for 15 minutes, 3 times a day. He also had them look at rapid-fire images of hands and identify whether they were right or left hands, a cognitive task proven to activate the motor cortex. By engaging the brain's motor programs without actually moving the muscles, the patients slowly rebuilt their neural maps. Once the maps were restored, they transitioned to the mirror box. Astonishingly, using nothing but imagination and visual illusion, half of these chronic, intractable pain sufferers experienced a complete cessation of their symptoms. The revelation that pain is a dynamic, plastic construct of the brain has revolutionized surgical medicine. We now know that the trauma of a surgeon's scalpel can physically alter the brain's pain maps, hardwiring post-operative agony into the patient's nervous system. To prevent this dark plasticity, anesthesiologists now administer local nerve blocks and painkillers before the patient is put to sleep with a general anesthetic. By completely severing the communication between the tissue and the brain prior to the incision, they prevent the pain maps from ever registering the trauma, radically reducing the incidence of chronic post-operative pain. Ramachandran's worldview effortlessly bridges the rigorous science of Western neurology with the profound mysteries of his Indian upbringing. Growing up, he witnessed yogis walking barefoot across hot coals and men in deep trances driving needles through their flesh without wincing. In the West, such feats are often dismissed as parlor tricks, but Ramachandran recognizes them as profound demonstrations of neuroplasticity. A trance is simply the brain exercising its magnificent power to definitively slam shut the gates of pain. By understanding that our perception of the world and our experience of our own suffering is an illusion constructed by the plastic brain, Ramachandran has given us the tools to rewrite the code of our own reality. He proves that the imagination is not merely a theater for daydreams, but a biological force capable of reshaping the physical architecture of the mind, turning off the darkest alarms of the nervous system and offering salvation to those trapped in the prison of their own neurobiology. Chapter 8. Imagination. How thinking makes it so. The profound divide between the tangible flesh of the human body and the ethereal realm of thought has puzzled philosophers for centuries. René Descartes famously split the human experience into 2 distinct domains, the physical body, which he viewed as an intricate machine, and the immaterial mind, which floated ghost-like within the machine, operating it from a mysterious distance. For hundreds of years, mainstream science accepted this Cartesian divide, treating thoughts as fleeting, weightless phenomena that left no physical trace on the brain's permanent architecture. But in the laboratories of modern neuroscience, this ancient boundary has completely dissolved. We now know that an invisible thought is not merely a passing shadow in the mind, it is a profound, physical sculptor of the brain's very anatomy. At Harvard Medical School, the brilliant Spanish-born neurologist Álvaro Pascual Leone designed an elegant experiment that beautifully demonstrated the astonishing weight of pure imagination. He sought to understand if the mental rehearsal of an action could physically alter the brain in the same manner as physical practice. He gathered a group of volunteers who had absolutely no prior experience with playing a musical instrument and seated them in front of a piano. He instructed half of the group to physically practice a simple 5-finger piano exercise for 2 hours every day over the course of 5 consecutive days. The other half of the group was given a far more unusual task. They were instructed to sit perfectly still before the keyboard and merely imagine playing the exact same sequence of notes. They were strictly forbidden to move a single muscle in their hands. To observe the inner workings of their minds without resorting to surgery, Pascual Leone utilized transcranial magnetic stimulation, or TMS. This revolutionary device resembles a thick magnetic wand that, when held directly over a subject's skull, passes a focused magnetic pulse harmlessly through the bone and into the cerebral cortex. By carefully firing this pulse over specific regions, researchers can temporarily stimulate or inhibit neural circuits, causing a patient's thumb to twitch or a finger to curl. It acts as an incredibly precise, non-invasive cartography tool, allowing scientists to draw highly detailed maps of the brain's motor functions in real time. As the days progressed, the brain maps of the volunteers who physically struck the keys expanded predictably. The neural territory governing their fingers rapidly grew, colonizing adjacent areas of the motor cortex as they learned the new skill. However, the true revelation occurred when Pascual Leone mapped the brains of the volunteers who had only engaged in mental practice. Their brain maps had expanded to the exact same degree. The sheer act of sustained, focused imagination had triggered a profound biological reorganization. The neural pathways of the mind cannot fundamentally distinguish between an action performed in the physical world and an action vividly simulated in the theater of the imagination. To confirm the physical validity of these newly forged mental circuits, Pascual Leone asked the mental practitioners to finally touch the keys. Astonishingly, they could play the sequence with a high degree of proficiency. Their brains had already laid down the necessary neurological infrastructure. Though they required a brief period of physical practice to match the fluid, automatic perfection of the first group, their minds had effectively mastered the physical task through thought alone. The implications of mental practice extend far beyond the acquisition of complex motor skills. They delve into the raw generation of physical power. For generations, elite athletes and performers have relied on visualization, intuitively sensing that vividly imagining a perfect performance brings them closer to achieving it. Science has now provided the biological foundation for this intuition. The researcher Guang Yue conducted a study focusing on the simple, brute act of muscle contraction. He asked individuals to merely imagine powerfully flexing the muscles of their little finger. After several weeks of pure mental exertion, without the subjects ever lifting a physical weight or moving the digit, the physical strength of their fingers increased by a staggering 22%. This ghostly acquisition of strength is a testament to the fact that physical power is not solely the domain of muscle mass. It is fundamentally an expression of neurological efficiency. When a person imagines a physical movement, the brain's motor programs run a perfect invisible rehearsal. The neurons fire in the exact sequence required for the action, though the final command to move the muscle is suppressed just before it reaches the limb. Through this vivid mental rehearsal, the motor neurons become exceptionally synchronized. When the individual finally decides to execute the physical movement, the brain delivers a massively concentrated, highly coordinated electrical signal to the muscle, resulting in a dramatic, measurable increase in physical force. Pascual Leone's exploration of the brain's dynamic architecture led him to further investigate the sheer speed at which these plastic changes occur. In another groundbreaking study, he blindfolded healthy, sighted volunteers for 5 consecutive days. Stripped of their primary sensory input, the volunteers were placed in an immersive environment and intensely trained in reading Braille. After just a few days of total darkness, brain scans revealed something seemingly impossible. The visual cortex, the massive region at the back of the brain normally dedicated entirely to processing light and imagery, had been hijacked. It was now actively processing the tactile sensations arriving from the volunteers' fingertips. This rapid, almost instantaneous reorganization posed a severe biological puzzle. Brain tissue cannot physically sprout millions of new axonal connections across vast cortical distances in a matter of mere days. To explain this phenomenon, Pasquale-Leone theorized that the brain must possess two distinct mechanisms for neuroplastic change. The first is rapid and functional, the unmasking of existing dormant pathways. He proposed that the visual cortex naturally possesses weak secondary neural connections to the tactile and auditory systems. Normally, the overwhelming continuous flood of visual data suppresses these faint signals. But the moment the blindfold is applied and the visual noise ceases, the brain immediately unmasks the hidden tactile pathways, allowing the visual cortex to step in and help process the complex shapes of the braille. However, this rapid adaptation was deeply fragile. When the blindfolds were removed on a Friday afternoon, the volunteers' brains rapidly reverted to their original state. By Monday morning, the visual cortex had entirely abandoned its temporary tactile duties and returned to processing sight. The rapid functional unmasking was completely reversible, yet if the volunteers continued to practice Braille daily for several months, the changes solidified and became permanent. The brain transitioned from merely unmasking old roads to aggressively paving new ones. Millions of new synaptic connections physically sprouted, creating a hardened structural change that persisted even when the volunteers were not actively practicing. The profound lesson hidden within these elegant experiments is that the brain is an organ in constant flux, continuously reshaping itself in direct response to the demands of our attention. Every thought we entertain, every scenario we vividly imagine, and every mental habit we cultivate leaves a physical footprint upon our neural architecture. We are not merely passive operators locked inside a biological machine. We are the active architects of our own minds. By wielding the silent, invisible power of our own contemplation, we possess the terrifying and beautiful capacity to sculpt the physical reality of our brains. Chapter 9. Turning Our Ghosts into Ancestors. Psychoanalysis as a Neuroplastic Therapy. For over 4 decades, a man known to his doctor as Mr. L had been shadowed by recurring heavy depressions and a bewildering inability to maintain relationships with women. By the time he sought psychiatric help in his late 50s, having recently retired, the prevailing medical wisdom of the early 1990s offered little optimism. The scientific consensus held that a man approaching 60 was biologically entrenched in his habits. The structure of the adult mind was thought to be entirely rigid, making any therapy that aimed to alter the fundamental bedrock of a person's character seem like a futile endeavor. Mr. L presented himself as a highly intelligent, polite, yet profoundly remote individual. His speech was clipped and spare, utterly devoid of emotional resonance. Alongside his chronic melancholy, which only partially responded to medication, he experienced terrifying, unprovoked episodes of mental paralysis. During these spells, he felt entirely numb, stripped of all purpose, as though the forward march of time had suddenly halted. To cope, he frequently turned to alcohol, yet his greatest distress centered on his romantic life. The moment he grew close to a woman, an irresistible urge to withdraw would overtake him, accompanied by the persistent nagging conviction that a more ideal, perfect woman was waiting for him elsewhere. He was chronically unfaithful, a pattern of behavior that had destroyed a marriage he had genuinely valued. He found himself incapable of understanding love or jealousy, feeling only that women ultimately wanted to trap and possess him. Even his devotion to his own children felt more like a dutiful obligation than a source of spontaneous, joyful affection. The roots of this emotional desolation stretched back to a catastrophic rupture in his early childhood. When Mr. L was a mere 26 months old, his mother died giving birth to his younger sister. Raised on an isolated, impoverished farm during the Great Depression, his family endured the tragedy with stoic silence. A year later, the young boy developed a severe gastrointestinal illness. Unable to care for a sick toddler alongside his other siblings, his grieving father sent the 4-year-old boy to live with a childless aunt 1,000 miles away. In the blink of an eye, the child was stripped of his mother, his father, his siblings, his health, and every familiar comfort of his physical world. As an adult, Mr. L insisted that these events had left no lasting mark on his psyche. He possessed no conscious memories from before the age of 4 and argued that a toddler's mind was simply too undeveloped to register such profound grief. He never cried. He spoke of his childhood devastation with a chilling detachment, as though recounting the biography of a stranger. Yet, beneath the surface of his conscious denial, his nervous system was continuously sounding an alarm. He looked like a man trapped in a state of perpetual shock. More tellingly, his nights were plagued by a recurring static dream. In the dream, he was endlessly searching for a lost toy in the dark, feeling that the toy was of immense value and that he would instantly recognize it if he could just find it. To understand how such an early trauma could become biologically locked within Mr. L's brain and how it could eventually be unlocked, one must look to the pioneering molecular research of the neuroscientist Eric Kandel. Working with the giant marine snail Aplysia, Kandel demonstrated that learning and memory physically alter the cellular structure of the nervous system. When the snail was trained to anticipate a mild shock, its neurons underwent a profound transformation. Kandel discovered that the transition from a short-term memory to a long-term memory requires the synthesis of new proteins within the cell. A chemical messenger travels into the nucleus of the neuron, activating specific genes that then direct the growth of new synaptic connections. A single neuron, upon learning a new long-term memory, might double its number of synaptic connections. This same microscopic alchemy occurs in the human brain. Every time we learn, we alter gene expression. While we cannot change the genetic templates passed down from our ancestors, our thoughts, experiences, and environments dictate which of those genes are transcribed and actively utilized to build our neural architecture. When psychotherapy helps a patient change, it does so by facilitating a deep biological learning process. The therapeutic conversation literally speaks to the neurons, prompting changes in gene expression that forge new anatomical interconnections within the mind. Kandel's intense drive to understand the biological permanence of memory was forged in the crucible of his own traumatic childhood. Born in Vienna in 1929, he witnessed the terrifying ascent of the Nazi regime. Following the annexation of Austria, his classmates instantly shunned him because he was Jewish. On the night of his 9th birthday, the horrors of Kristallnacht erupted. His father was arrested, their home was ransacked, and the toys he had just received were looted. The visceral, unshakable nature of these memories drove Kandel to dedicate his life to discovering exactly how the brain burns such experiences into its permanent circuitry. Long before Kandel observed these changes through a microscope, Sigmund Freud anticipated the neuroplastic nature of the mind. Freud theorized that memories are not perfectly preserved, static artifacts stored in a mental vault. Instead, they are dynamic and subject to constant revision. As we mature and encounter fresh circumstances, our early memories are retranscribed, taking on new meanings and emotional weights based on our current understanding of the world. However, catastrophic traumas experienced in infancy, like those suffered by Mr. L, are not easily accessed by the conscious mind, and thus they resist this healthy retranscription. Because the infant's explicit narrative memory system is not yet fully developed, the trauma is stored primarily in the procedural memory system, the brain's automatic unconscious repository for emotional reactions and survival behaviors. Freud discovered that these buried unconscious memories could be brought to the surface through a phenomenon he called transference. In the quiet, neutral environment of psychoanalysis, patients inevitably begin to project the emotions, expectations, and relational patterns of their earliest childhood figures onto the analyst. They do not merely remember the past, they unwittingly relive it in the present. In his therapy, Mr. L began to exhibit these transferences. He would frequently fall into mysterious, silent depressions immediately preceding weekends or the analyst's vacations. Slowly, he recognized that these minor interruptions in his care were triggering the exact same procedural memories of despair and paralysis that he had experienced when he was abruptly separated from his family. For the first time in his life, he consciously linked his agonizing adult sense of searching with the catastrophic, unmourned loss of his mother. By bringing this unconscious connection into the light of conscious attention, he began the arduous neuroplastic work of unwiring it. As his defensive walls began to crack, his dreams shifted. He dreamt of standing with another man who was helping him move a heavy wooden box. As they moved it, the man pointed out a terrible scarred deformity on Mr. L's leg, remarking on the devastating price Mr. L had paid for the box. Mr. L associated the wooden box with both his lost toy box and a coffin. He realized he was carrying the dead weight of his mother's passing. The scarred leg represented his profound emotional wounding. This dream precipitated a massive breakthrough. Reflecting on the heavy price he had paid, Mr. L realized why he relentlessly sabotaged his romantic relationships. His compulsion to leave women to search for an ideal partner was not driven by arrogance but by a tragic unconscious loyalty. The phantom, perfect woman he was endlessly searching for was the vague, idealized memory of his lost mother. To deeply love a living woman felt to his unconscious mind like a betrayal, an abandonment of his devotion to the mother who had died bringing his sister into the world. His chronic infidelity was a twisted manifestation of absolute heartbreaking fidelity to a ghost. Recognizing this, the dam broke. The man who had not shed a tear since early childhood wept uncontrollably. Over months of therapy, he endured intense periods of emotional regression, re-experiencing the raw, agonizing grief of the abandoned toddler. He wailed for his mother with the physical intensity of a small child. This was not merely an emotional release. It was a profound neuroplastic unmasking. To rewire a deeply entrenched defensive neural network, the brain must often bypass the hardened circuits of adulthood and activate the older, dormant pathways of childhood, allowing the original emotional data to be processed anew.
Chapter 10. Rejuvenation. The discovery of the neuronal stem cell and lessons for preserving our brains. For over a century, a bleak and unyielding doctrine governed the field of neuroscience, casting a long shadow over our understanding of human aging. It was decreed by Santiago Ramon y Cajal, the brilliant founding father of modern neuroanatomy, who painstakingly mapped the intricate forests of the nervous system. Cajal declared that in the adult brain, nervous paths are fixed, ended, and immutable. Everything may die, he asserted, but nothing may be regenerated. This grim decree became the absolute law of biology. We were taught that we are born with a massive, finite inheritance of brain cells, and from the moment of birth we enter a slow, irreversible state of neurological decay, squandering our cognitive inheritance day by day. This dogma was so deeply entrenched that when a young researcher named Joseph Altman published evidence in the 1960s showing that adult rats could indeed grow new neurons, a process called neurogenesis, he was not just ignored, he was scientifically exiled. His funding was cut, and his career was essentially derailed. The establishment simply refused to believe that the complex, delicate architecture of the adult mind could tolerate the chaotic birth of new cells. It was assumed that introducing raw, untamed neurons into a perfectly balanced neural network would erase existing memories and plunge the brain into chaos. The resurrection of this forbidden idea began far from the human cortex in the cheerful, whistling throats of canaries. Fernando Nottebohm, a researcher studying songbirds, noticed something extraordinary. Male canaries learn intricate new songs every spring to attract mates. Nottebohm discovered that the brain center responsible for learning these melodies actually doubled in size during the mating season, only to shrink back down in the winter. Investigating further, he realized the birds were not merely plumping up existing cells, they were actively giving birth to entirely new neurons. The adult canary brain was continuously tearing down and rebuilding its own hardware to accommodate new learning. The scientific community, though fascinated, maintained the firewall between species. They argued that while a bird might possess this capacity to adapt to seasonal demands, the superior, vastly more complex human brain could not possibly risk such anatomical turnover. The wall finally crumbled in 1998, thanks to the persistent work of Fred Gage and Peter Eriksson. To prove that human neurogenesis was real, they relied on a poignant and daring experiment involving terminal cancer patients. These patients had volunteered to be injected with a chemical marker called BRDU, which attaches itself to the DNA of any dividing cell. It was primarily used to track the aggressive growth of tumors. But Eriksson and Gage knew that if the human brain was genuinely creating new neurons, those nascent cells would also absorb the marker. When the patients eventually passed away, their brains were examined. The researchers looked deep into the hippocampus, the seahorse-shaped structure vital for memory consolidation and spatial navigation. Under the microscope, illuminated by fluorescent dye, the truth was undeniable. Mixed among the ancient, lifelong neurons were bright, newly born cells. The patient's brains, even in the twilight of terminal illness, had been actively generating new neurons until the very end. The discovery of the neuronal stem cell completely rewrote our understanding of the aging brain. We now know that the hippocampus is a biological nursery producing thousands of new neurons every day. These fresh, highly plastic cells are essentially blank slates, possessing an extraordinary capacity to adapt and wire themselves into existing neural networks.
But this remarkable capacity is not unconditional. Just as the brain requires specific conditions to learn, the neuronal stem cell requires specific conditions to survive. The daily birth of new neurons is merely the first step. Whether these cells live or die depends entirely on the environment they enter and the demands placed upon them. Research has unveiled a clear set of principles for cultivating and preserving these vital new cells. Physical exercise is perhaps the most potent biological trigger. Studies show that when animals run on exercise wheels, the rate of neurogenesis in their hippocampi explodes. Aerobic activity floods the brain with blood and essential growth factors, creating a deeply fertile environment for cell division. The brain essentially interprets physical movement as a signal that the organism is exploring new territory, thereby demanding new spatial memories and increased cognitive capacity. Conversely, the most devastating enemy of neurogenesis is chronic stress. When we are subjected to prolonged, inescapable stress, the adrenal glands release high levels of cortisol, a hormone designed for short-term survival. In the long term, cortisol acts as a biological toxin to the hippocampus. It literally halts the production of new stem cells and actively kills existing neurons. This neurological massacre explains why individuals suffering from chronic depression or trauma often experience significant memory loss and a profound inability to learn new emotional patterns. Their hippocampal nurseries have been temporarily poisoned. Remarkably, this understanding provides a new neuroplastic explanation for how certain psychiatric medications function. It is increasingly believed that antidepressant drugs do not merely correct chemical imbalances in the synaptic cleft. Rather, they stimulate the hippocampus to resume the production of new neurons. The medication rescues the brain from the neurotoxic effects of stress, allowing the mind to literally rebuild its physical capacity for resilience and joy. The survival of these newly minted neurons is also intimately tied to cognitive exertion. If an animal generates new cells through exercise but is then placed in an impoverished, unstimulating environment, the majority of the new neurons quickly wither and die. To integrate into the brain's complex architecture, the newborn cells must be aggressively recruited by rigorous learning. The brain obeys a ruthless economy. Neurons that are not actively fired are swiftly eliminated. This biological reality offers a profound lesson for the second half of human life. The traditional model of retirement, characterized by a sudden cessation of challenging work and a retreat into predictable, effortless routines, is neurologically disastrous. To preserve the brain's mass and cognitive agility, we must continually subject ourselves to novel, demanding mental tasks. We must provide the newly born neurons with a reason to live. Learning a new language, mastering a complex musical instrument, or navigating unfamiliar physical terrain provides the critical neurological tension required to stitch the fragile stem cells into the permanent fabric of the mind. We are not the helpless victims of inevitable cognitive decay. Nature has equipped us with a perpetual source of biological renewal. The aging brain is not a dying machine. It is a dynamic, living ecosystem that remains intensely responsive to the physical and mental demands we choose to place upon it. By aggressively cultivating our physical health and relentlessly challenging our intellect, we possess the remarkable, lifelong ability to rejuvenate our own minds.